normal light is passed through some nickel prism or analyzer, it gives rise to plane polarized light. And one thing we should observe here that normal light is unidirectional. It can vibrate in all the planes, whereas plane of polarized light is unidirectional and it can pass or it can vibrate in only one plane. Here friends, optical isomerism. Today our main topic is optical isomerism, and in this optical isomerism we heard a word that is plane polarized light. Now let us discuss what is ordinary light and what is plane polarized light. Here ordinary light vibrates in all planes, whereas polarized light vibrates only in one plane. Here is a figure friends, we can observe clearly. This is the normal light which is vibrating in all the planes, and here is a plane polarized light which is vibrating in only one plane. And here is the activity for that. First we have considered a normal light friends which is multidirectional, and when it is passed through some nickel prism or analyzer, it gave rise to some light that is plane polarized light which is unidirectional. And when this plane polarized light is passed through some optically active substance, it rotates the plane of polarized towards right or towards left. This optically active solution or substance can rotate the plane of polarized light towards right or towards left. Here the phenomenon of rotation of plane of polarized light is visible, and we are saying that this polarized light can be rotated towards right and towards left. That means the compound which can rotate the plane of polarized light towards right side is called as dextrorotatory, in which dextro is a Latin word which means right and is represented by the prefix d or plus, and the compound which can rotate the plane polarized light towards left side is called as levorotatory, which means left and is represented by the prefix L or minus. Here by this we can observe that there are existence of two isomers takes place. One is D isomer and the another is L isomer. D isomer is nothing but which is rotated towards right side, and L isomer is nothing but which is rotated towards left side. Friends, we can see here D and L isomers. D isomeric substance rotates the plane of polarized light towards right, and its L isomer rotates towards left. Friends, here we can observe two isomers, one is D isomer and the another is L isomer, and which can measure this angle of rotation friends? Yes, there is a instrument which can measure this angle of rotation, that is nothing but polarimeter. Friends, all of you see here we can observe a polarimeter here. This is called as polarimeter, and in this tube we can fill some optically active substance, and when a normal light is placed here, we can observe from here this normal light, when it is passed through some nickel prism, it converts this normal light into plane polarized light, and this plane polarized light when passed through some optically active substance which is filled in this tube, and that optically active substance can rotate this plane polarized light towards right or towards left. This is called as polarimeter. By this we can define the polarimeter as a polarimeter is a scientific instrument which can measure the angle of rotation of plane of polarized light when it is passed through some optically active substance. Friends, we all discussed about coordination number, right? The coordination number is nothing but the ligands, how many ligands are bonded with the central metal atom is nothing but the coordination number of that complex. Here this optical isomerism is rarely expected in the complexes having coordination number 4 and coordination number 6. Let us see the coordination number 4 complexes. Here, before that, let us see some optical isomers. These are stereoisomers that are non-superimposable mirror images of each other. These are also called as enantiomers. Friend, here we can see a D isomer. When it is looked in a mirror, it looks like its L isomer. See friends, here our hands are the best example for optical isomers or enantiomers. Why? Because when we see our right hand in the mirror, it will same look like our left hand, right? Whenever see in the mirror in your face in your mirror, first once you see your right hand, it same looks like your left hand. That means our right hand and our left hand are the mirror images of each other, and if we place our left hand on the top of the right hand, we can observe clearly that these are non-superimposable on each other. Friends, are you observing here? My two hands, when they are kept on the top of each other, they are non-superimposable mirror images. These non-superimposable mirror images are nothing but optical isomers, are also called as enantiomers, are also called as enantiomorphs. Here, these enantiomers are stereoisomers that are non-superimposable mirror images of each other. These are also called as enantiomers and also enantiomorphs. Here enantiomers, these are non-superimposable mirror images. Here we can see friends, one is D and one is L. When they are looked in a mirror, they are mirror images of each other which are non-superimposable on each other. Friends, if we keep this isomer on the top of this isomer, here is nitrogen and here is a chlorine. That means we can clearly say that these are non-superimposable mirror images of each other. These have almost same physical and chemical properties, but they differ in rotation of plane of polarized light and also rate of reaction. Here I already said an example of our hand. If we look our left hand in the mirror, it is same looking like our right hand. And here is another example friend, a D isomer. Let us assume this isomer as D isomer, and when it is looked in the mirror, it seems look like L isomer. So these isomers are non-superimposable mirror images of each other. Friends, then what are the conditions for a substance to be optically active? Yes, there are some conditions for a substance to be optically active. That is, the first one is nothing but a substance or a molecule must be a chiral molecule, and the second one is nothing but it should not contain any element of symmetry. The first one is nothing but a molecule or a substance must be a chiral molecule, and the second one is it should not contain any element of symmetry. There are two elements of symmetry. One is plane of symmetry and the second one is center of symmetry. Let us see friends the conditions for optical activity. A complex must be chiral and it should not contain any element of symmetry. And what is chirality? We are saying that a molecule is a chiral molecule. What is chirality? Let us see. A molecule is chiral if it is not superimposable on its mirror image. Chiral is nothing but dissymmetric friends. A molecule is chiral if it is not superimposable on its mirror image. Most chiral molecules can be identified by their lack of plane of symmetry or a center of symmetry. These two are elements of symmetry. I already said that your hand is a chiral object as it does not have either of these types of symmetry. Now friends, let us speak about racemic mixture. Racemic mixture is a compound which is equimolar mixture of D and L isomers. This racemic mixture is optically inactive due to internal compensation, and this compound is nothing but, or this mixture is nothing but racemic mixture. Now let us see, we already said that the compounds or complexes containing coordination number 4 and 6 can exhibit optical isomerism. Here optical isomerism of complexes containing coordination number 4. In coordination number 4, square planar complexes and tetrahedral complexes exhibited. In square planar complexes, they do not show optical activity due to the presence of plane of symmetry. Friends, here we can see an example. Here is a compound which is called as tartaric acid. This is optically inactive, friends. Why? Why? Because it contains plane of symmetry. What is plane of symmetry? If a molecule, if it is cut into two equal parts, or if it is divided into two equal parts, they can be mirror images of each other. That means if we cut this molecule here into two equal parts and one equal part is in front of the mirror, it same looks like the second part. That means these are superimposable mirror images. So that here, due to plane of symmetry, this tartaric acid is optically inactive. Let us see what is center of symmetry in another molecule. If we see here is a center point, and if we draw a line to some distance and proceed that line into the opposite distance, we can find the same distance here, and that 2 points can meet the identical points in a molecule. This is nothing but center of symmetry, friends. And here we are saying that the tetrahedral complexes which contain 4 different ligands and show optical activity. And here square planar complexes, they do not show optical activity due to the presence of plane of symmetry. And in tetrahedral complexes having 4 different ligands, they show optical activity of type MABCD. And one thing we have to observe here, that tetrahedral complexes are expected, but till now there is no isomerism isolated, friends. But here is an example. In tetrahedral complex which contain unsymmetrical bidentate ligand exhibit optical activity. Here we can see the example of bis benzoyl acetoberyllium 2 ion, friends. Here these are non-superimposable mirror images, but till now no one isolated these two isomers. Now friends, let us see tetrahedral complex which contain symmetric bidentate ligand does not exhibit optical activity. Friends, here let us see an example. We are saying that tetrahedral complex which contain symmetric bidentate ligand, that means that is the type of MAA taken twice in the complex. Here this is bidentate ligand. Let us first discuss about a bidentate ligand. A bidentate ligand means a ligand which can donate 2 pairs of electrons to the central metal atom. These ligands are of many types: unidentate or monodentate, bidentate, tridentate, tetradentate, polydentate. What is the difference between these ligands means? A monodentate ligand can donate only 1 pair of electrons to the central metal atom, whereas bidentate ligand can donate 2 pairs of electrons to the central metal atom, and tridentate 3 pairs of electrons, and so on. And this central metal can accept the pair of electrons from the ligands. Here for tetrahedral complex having the formula MAA taken twice, here is an example, that nickel ethylene diamine taken twice. If we see the isomerism here, nickel has, it is tetrahedral, and the formula of ethylene diamine is NH2NH2 CH2CH2, and here the same thing repeats because there are two bidentate ligands. Here friends, NH2, CH2, CH2 and NH2. If we cut this molecule into 2 equal parts, what we can observe, friends? The same thing was repeated here and here. That means there is plane of symmetry in these compounds. That is called as internal plane of symmetry. Friends, this is the mirror and this is the first part and this is the second part of this molecule. If we observe this molecule, it can be seen that the first part is the mirror image of the second part and they are also superimposable mirror images. Therefore, in tetrahedral complexes containing the formula MAA taken twice does not exhibit optical isomerism. Now, let us see here friends. The following type of octahedral complexes exhibit optical isomerism. The types are M, A, B, C, D, E, F. Here M denotes the central metal atom and the A, B, C, D, E, F denotes the ligands which can donate only one pair of electrons each. And here the second one is MAA taken 3 type and the third one is MAA taken 2 and A 2 times. That means here small letter indicates that is a monodentate ligand and the capital letters indicates that they are bidentate ligands. And the another type is MA2, B2, C2 which are monodentate ligands but they are in number 2. Let us see the examples of these complexes. Here is an example of MABCDEF type of complex, that is we can observe here friends the 2 isomers, one is D isomer and the another is L isomer, and this D isomer is the mirror image of this L isomer, and when this D isomer is observed in the mirror, it seems look like its L isomer and they are non-superimposable on each other. Here we can observe that here is the pyridine and here is N2O, and if we place this D isomer on the top of the L isomer, they are not superimposable. Here we are taken an example, they are not superimposable on each other. By this we can say that MABCDEF type of complex clearly exhibits optical isomers. And the next one is MAA taken 3 type of complex. Here is an example, that is tris-ethylene diamine cobalt 3 chloride. Friends, here in this we can observe the isomers, one is D isomer and the one is L isomer. When these isomers are looked in the mirrors, they are mirror images of each other and also they are non-superimposable mirror images of each other. In this structure, chlorine ions are omitted, and here the dark line represents that these ions are closer to the viewers, that are V, and here the dotted lines represent that they are far away from the viewers. That means by this we can say that MAA taken 3 type of complex clearly exhibits optical isomerism, and here MAA taken 2 and A2 type of complex. For example, cis dichloro bis ethylene diamine cobalt 3 ion. Here we can see clearly they are mirror images of each other. One is cis D isomer and the another is cis L isomer. They are mirror images of each other. By this we can say MAA taken twice A2 type of complex exhibits clearly optical isomerism. And the fourth one is MA2, B2, C2 type of complex. Here is an example, and see the structures friends. Here these two are, one is cis D isomer and the one another is cis L isomer. When they are looked in the mirrors, they are non-superimposable mirror images of each other. By this we can say that MA2, B2, C2 type of complexes are clearly exhibits optical isomerism. Friends, here is a special type of isomer which is only the cis form of it is optically active and the trans form of is optically inactive. Here we can see friends, due to the presence of symmetry, trans dichloro bis ethylene diamine cobalt 3 ion is optically inactive. If we separate them, they have plane of symmetry, so they are not optically inactive. And here is assignment for you friends. Explain different types of isomerism exhibited by coordination compounds, giving suitable examples. Here we already discussed all the isomers and the examples. So, I think you all have heard this isomerism clearly, and I think you will submit the notes to your teacher. And the second one is give evidence that these two isomers are ionization isomers. Friends, one thing we have to observe that ionization isomers are differs in their ionizable ions. Friends, here let us recall what all we have discussed today. We have discussed about simple salt and addition compounds, and these addition compounds are again divided into two types. One is double salt and the another is coordination compounds, and we are also discussed that coordination compounds are of three types. One is anionic, the second one is cationic, and the third one is neutral. And in this coordination compound what are present? In this coordination compound a central metal atom, ligands, coordination pair and counter ions are present. That also we have learned. And when coming to isomerism, we learned a lot about isomerism today. In isomerism there are two types, one is structural and the another is stereo, and this structural again divided into four types, that is ionization, hydration, linkage and coordination isomers. And stereo isomerism is again divided into two types, that is geometrical and optical isomerism. And today we mainly focused on optical isomerism, and we discussed about plane of polarized light and the differences between normal light or ordinary light and plane of polarized light. And we also saw a polarimeter in which we can measure the rotation of plane of polarized light, and by this rotation we can exhibit two isomers, that is one is D isomer and the another is L isomer. D isomer, the compound which can rotate the D isomer is called as dextrorotatory, and the compound which can rotate the plane of polarized light towards left is called as levorotatory. And the conditions for a substance to be optically active are, the first one is a molecule must be a chiral molecule, and the second one, it should not contain any element of symmetry. And we also discussed that the coordination compounds containing the coordination number 6 and 4 can exhibit optical isomerism, and in the complexes having coordination number 4, square planar complexes and tetrahedral complexes are expected or exhibited. In that square planar complexes there is no isomer because due to plane of symmetry, whereas in tetrahedral complexes we are expecting some isomers, but till now there is no isomerism isolated. And whereas in the complexes containing coordination number 6 we have several examples, and also we have discussed about that several examples. Friends, today we also learned about enantiomers. Enantiomers is an important bit for IPE. They may ask what is enantiomerism. What is enantiomerism, friends? Enantiomerism is nothing but optical isomerism, in which compounds having same molecular formula but they differs in the rotation of plane of polarized light. Here this rotation of plane of polarized light is of two types, one is D and one is L. Here D isomers are the compound rotates the plane of polarized light towards right side, and whereas in L isomers the compounds rotates the plane of polarized light towards left side. Friends, now let us see again what is ionization isomerism. Here this type of isomerism arises due to the difference in ionizable ions. Here we can find the two compounds which have same molecular formula but they differs in their ionizable ions. Because due to here the sulphate ions is present outside the coordination sphere and here the sulphate ions are present inside the coordination sphere. Due to this small difference, this ionization isomerism arises, and due to this small difference they gives rise to the two different ions. And next one is hydrate isomerism. Isomers of crystalline complexes that differ in whether water is present inside or outside of the coordination sphere. Here we can observe three compounds, friends. One is in first one the total water molecules are present inside the coordination sphere, and in the second one we can observe clearly 5 water molecules are inside the coordination sphere and the one water molecule is outside the coordination sphere. And in the third example we can find 4 water molecules are inside the sphere and 2 water molecules are outside the sphere. By this little difference they gave rise to different color, friends. The first one gave rise to violet color and the second one gave rise to blue green color, whereas the third one gives rise to dark green color. Now let us see what is linkage isomerism. This type of isomerism arises in the coordination compounds containing ambident ligand. We already discussed what is ambident ligand. What is ambident ligand, friends? An ambident ligand is a monodentate ligand which have two different donor atoms. Here we can observe clearly to this compound. Hello? Hello? Hello?
Hello.
Hello Swero. Hi, good afternoon.
Good afternoon, sir.
Good afternoon. What's your doubt?
Yes, sir, from Suryapet.
Okay. What's your question?
Why is geometrical isomerism not possible in tetrahedral complexes?
A good question, Swero. Why is tetrahedral complexes not exhibit in geometrical isomerism? It is not related to my topic. My topic is optical isomerism, even though I can clear your doubt, friend. Here geometrical isomerism in tetrahedral complexes does not exhibits because due to the plane of symmetry. Have you cleared your doubt, friend?
Okay, thank you, sir. Okay, thank you, sir.
Thank you. Now let us see here about linkage isomerism. This type of isomerism arises in the coordination compounds containing ambident ligands. And here the next one is coordination isomerism. In this coordination isomerism we can find two different spheres. One is anionic sphere and the another is cationic sphere, and the random exchangement of ligands. Friends, I think you have learned a lot from this lesson, and you are going to attempt any competitive examinations. This chapter or this topic is going to give you a boost and give nothing confusion in the examination while you are attempting any questions. Friends, now my topic is concluded today, and I thank to my parents who gave birth to me, and special thanks to my principal Anantalakshmi ma'am and my sirs Karnakar Reddy sir and Yatiraj sir and whole the staff of COE who encouraged me a lot to be here, and a special thanks to Secretary sir because he was I am here. Thank you. Have a nice day.